Think fast. Which planet will this particle crash into? It's not an easy question. If you said the green one, you're right. But it's hard to foresee this trajectory. Moving the starting point only a little bit causes huge changes in behavior. We know for sure that the ones which start sufficiently close to each planet will indeed crash into it, due to a lack of energy to escape that planet's gravity well. But that reasoning only goes so far. It's a mess when we look at points far away from the planets. This is not a problem with a clean solution. There's no simple equation here to tell you. I'll just go ahead and spoil the pattern. This plot shows if an object is dropped at each point, the planet which it would crash into. There's a lot of emergent complexity going on here. Let's watch an object at every point fall. Wow, check that out. We can also move around the planets and see how the plot changes. If their shape is symmetric, so is the plot. We can play around with some different shapes and watch what happens to the design. Now, those who know a thing or two about physics could probably tell you that if these gravitational attractors are actually points, then in reality you should never actually crash. You might fall into a stable orbit or spin around chaotically forever, but your kinetic energy wouldn't dissipate enough to cause your orbit to decay into a crash. And that's true. I am slightly cheating here. I'm applying a constant force, a drag per se, which slows the particles down. Let's mess around with this parameter and see what happens. Check that out. Perhaps unsurprisingly, the greater the drag, the less complicated the orbital patterns are, because each particle will just slowly march to the nearest attractor. As drag decreases, the more time the object spends winding in complicated orbits before its fate is decided, and thus the more scrambled the colors get.